Across the quiet universe, there are places where light enters the darkness and never returns. They cannot be seen directly, yet their gravity shapes stars, bends light, and quietly guides entire galaxies. We call them black holes, though the name reveals almost nothing about what they truly are. To understand their mystery, we must begin long before the darkness forms, inside the heart of a living star. A star appears steady from far away, but its peaceful glow hides a continuous struggle against gravity. Gravity pulls every layer inward, always seeking to compress the star beneath the weight of its own matter. Deep within the core, nuclear fusion produces heat and pressure that push outward against this relentless inward force. For millions or billions of years, these opposing forces remain balanced, and the star continues to shine. The light reaching our eyes is part of that balance, released from a furnace hidden beneath countless layers of plasma. Inside the core, lighter elements are joined together, forming heavier elements and releasing enormous amounts of energy. That energy travels slowly outward before escaping into space as the familiar warmth and radiance of a star. Yet every star carries a limited supply of fuel, and even the brightest sun cannot shine forever. Smaller stars can fade gently, leaving behind dense remnants that cool across unimaginable stretches of time. The most massive stars follow a more violent path because their immense gravity demands a hotter and faster-burning core. They consume their fuel rapidly, building new elements in a sequence of increasingly brief and unstable stages. Their brilliant lives may be short by cosmic standards, but their final moments can transform the space around them. As a massive star ages, its core becomes layered like a vast furnace built from the ashes of earlier reactions. Hydrogen gives way to helium, and helium is followed by heavier elements formed under greater pressure and heat. Each new stage temporarily supports the star, delaying the collapse that gravity has been preparing from the beginning. Eventually, the central furnace begins producing iron, an element that changes the fate of the entire star. Fusing iron does not provide the useful energy needed to hold the core against the pressure of gravity. The star has reached a threshold where its ancient balance can no longer be maintained. Without enough outward pressure, the iron core begins to collapse beneath an almost inconceivable weight. Matter falls inward at tremendous speed, compressing the center into a smaller and denser region. The collapse unfolds in less time than a quiet breath, although the star may have lived for millions of years. Atoms are crushed together, and the ordinary structure of matter begins to break under the growing pressure. Electrons and protons can combine into neutrons, releasing a flood of nearly invisible particles called neutrinos. For a moment, the collapsing core may become one of the densest objects the universe can support. The outer layers continue rushing inward until they strike the compressed center and are violently thrown back. A tremendous shock moves outward through the star, carrying heat, radiation, and newly formed elements into space. The result can be a supernova, a stellar explosion bright enough to briefly rival the light of a galaxy. Within the expanding cloud, the star scatters material that may someday become planets, oceans, and living worlds. The explosion is spectacular, but the deeper mystery lies inside the compact remnant left behind. When the remaining core is not too massive, the resistance of densely packed neutrons can halt the collapse. The remnant then becomes a neutron star, holding more mass than the Sun within a region the size of a city. If the core is heavier, even this extreme form of matter may be unable to resist gravity. There is no explosion at the center that can restore the lost balance once the critical threshold is crossed. The core continues shrinking, and its gravitational field grows stronger as the same mass occupies less space. Soon, the escape speed near the collapsing object approaches the speed of light itself. When the boundary is finally crossed, a black hole has formed within the dying remains of the star. The black hole is not an ordinary object with a solid surface hidden beneath a layer of darkness. It is a region where space and time are curved so deeply that every possible path points inward. Its defining boundary is called the event horizon, the invisible line beyond which no signal can return. Nothing special may mark this boundary locally, yet crossing it changes every possible connection with the outside universe. Light emitted outside the horizon can still escape if it travels along a path leading away from the black hole. Light emitted inside the horizon cannot escape because the geometry of space-time no longer offers an outward path. This is why the darkness of a black hole is more profound than the absence of visible light. It is a separation between events that can reach us and events that are permanently hidden. Long before black holes were observed, thinkers wondered whether gravity could create an object too dark to see. Those early ideas imagined light as particles struggling to escape from the surface of an enormously compact star. The modern picture became possible only after gravity was understood as the curvature of space and time. In this deeper view, matter does not simply pull across space because matter changes the shape of space-time itself. Planets follow curved paths around stars because they move through geometry shaped by mass and energy. Light also follows this geometry, even though light has no rest mass and always moves at the same local speed. Near an extremely compact object, the curvature becomes so severe that light can circle, bend, or disappear inward. A black hole is therefore not merely something inside space, but a dramatic shape taken by space-time. The size of the event horizon depends mainly on the mass contained within the black hole. A black hole formed from a star may have a horizon spanning only a few dozen kilometers. That small region can contain several times the mass of the Sun, compressed beyond any familiar state of matter. Larger black holes possess wider horizons, yet their surrounding darkness can remain hidden against the darkness of space. A black hole does not reveal itself by shining, so astronomers search for the effects of its gravity. A nearby star may orbit an unseen companion whose mass is too great to be an ordinary faint object. The visible star moves in a regular pattern, quietly tracing the presence of something hidden beside it. From that motion, scientists can estimate the invisible companion's mass and test whether a black hole is the best explanation. Sometimes the black hole draws gas from a nearby star, creating a luminous structure called an accretion disk. The gas does not fall directly inward because its sideways motion causes it to spiral around the black hole. Friction and magnetic forces heat the disk until it glows with temperatures far beyond the surface of the sunday. The black hole remains dark, but the surrounding matter can become one of the brightest sources in the sky. Close to the horizon, the disk moves at a significant fraction of the speed of light. Light from the approaching side can appear brighter, while light from the receding side appears dimmer and redder. Gravity bends the image of the disk, allowing light from its far side to curve into view. The result is a distorted ring of fire surrounding a central shadow that marks the hidden region. Some feeding black holes also produce narrow jets that extend far above and below the glowing disk. These jets do not emerge from inside the event horizon because nothing can travel outward from there. Instead, magnetic fields near the rotating disk can redirect some incoming material before it crosses the boundary. The redirected particles race into space, carrying energy across distances much larger than the black hole itself. Many black holes are not actively feeding and may drift through the galaxy in almost complete silence. Without nearby gas or a companion star, a dormant black hole may produce very little detectable radiation. Its presence may be revealed only when its gravity bends the light of a distant background star. For a brief time, the distant star can appear brighter as the hidden object passes between it and Earth. A black hole can also reveal itself when it meets another compact object in the darkness. Two black holes may orbit each other for millions of years while slowly losing energy from their motion. Their orbit tightens, their speed increases, and the surrounding fabric of space-time begins to tremble more strongly. These traveling distortions are gravitational waves, faint ripples produced by accelerating masses. During the final moments, the two horizons rush together and merge into a single larger black hole. The merger releases an immense pulse of gravitational energy without producing light from the horizons themselves. When those waves reach Earth, they stretch and compress space by an amount smaller than an atomic nucleus. Sensitive instruments can detect this tiny motion and translate a distant collision into measurable evidence. Black holes are sometimes imagined as cosmic vacuum cleaners that drag everything in a galaxy toward destruction. In reality, their gravity follows the same basic rules as the gravity of any object with the same mass. A planet orbiting far away would continue along a stable path if its star were replaced by an equal mass black hole. The danger becomes extreme only near the horizon, where tidal forces and curved space-time dominate every possible journey. The creation of a black hole is not simply the destruction of a star, but a transformation of its gravitational presence. The star's former surface disappears, while its mass continues shaping the motion of nearby matter and light. Something once filled with glowing plasma becomes a region defined by a boundary that cannot be touched from outside. The universe has turned the remains of a star into a question about the deepest nature of reality. Beyond the horizon, our current theories predict a continued collapse toward a region of extraordinary density. Scientists do not yet know whether that prediction describes physical reality or signals the limits of existing theory. For now, the horizon remains the last boundary that observation can approach without crossing into permanent silence. In the next part of our journey, we will move closer to that boundary, where light bends and time begins to change. The black hole waits without movement, surrounded by stars whose light has traveled across the galaxy to reach its gravity. From a great distance, it may appear like a small absence within a much larger field of quiet light. Yet as we move closer, the darkness begins to reveal a complex architecture shaped entirely by curved space-time. The journey toward its horizon is therefore not simply a journey through space, but into a changing geometry. Far from the black hole, the surrounding stars appear almost ordinary, scattered across the familiar depth of the universe. Closer in, their positions begin to shift because their light follows paths bent by the black hole's gravity. A star hidden behind the darkness may appear beside it, above it, or even in several places at once. Nothing has happened to the distant star itself, but the road taken by its light has been transformed. This bending of light is known as gravitational lensing, one of the clearest signatures of curved space-time. A galaxy behind a massive object can be stretched into arcs, rings, or repeated images across the sky. Near a black hole, the same effect becomes far stronger because the curvature is concentrated within a much smaller region. The surrounding universe seems to fold around the darkness, turning distant starlight into a luminous and distorted frame. Some rays pass far from the black hole and are deflected only slightly before continuing into the distance. Other rays pass close enough to curve around the black hole before escaping along a completely different direction. A narrow family of paths can circle the black hole, although the smallest disturbance eventually sends the light away or inward. This unstable region is often called the photon sphere, around a simple and non-rotating black hole. Light near the photon sphere may travel around the darkness more than once before finally reaching a distant observer. Each additional orbit creates a thinner and fainter image nested close to the edge of the black hole's shadow. In principle, these delicate rings contain views of the same universe arriving along paths of very different lengths. The darkness is surrounded by echoes of light, layered together from moments that did not reach us at the same time. The dark region seen by a distant telescope is usually larger than the event horizon hidden within it. It is called the black hole shadow, a shape created by light paths that are captured rather than returned. Its boundary is outlined by highly bent radiation from hot matter and distant sources behind the black hole. We do not see the horizon itself, but we see the absence created when nearby paths disappear beyond it. When glowing gas surrounds the black hole, gravitational lensing allows us to see parts of the disk normally hidden behind it. Light from the far side bends over the top and beneath the bottom of the central shadow. A flat disk can therefore appear as a bright ring wrapping around a darkness with no visible surface. The image is not a simple picture of matter, but a record of many curved journeys taken by light. Motion within the disk changes the brightness even further as gas races around the black hole at extraordinary speed. The side moving toward us may appear brighter because its radiation is concentrated and shifted toward higher frequencies. The side moving away can appear dimmer and redder, even when both sides release similar amounts of energy. The apparent imbalance is a quiet reminder that speed changes how light is received across the universe. Gravity also changes the color of light as it climbs away from the black hole's deep gravitational field. Its wavelength becomes longer, and a distant observer measures the radiation as weaker and shifted toward red. This gravitational redshift grows stronger as the source approaches the event horizon from the outside. Near the boundary, each departing signal arrives with less energy, and after an increasingly long delay, the delay reveals that gravity affects more than the direction and color of light because gravity also affects time. A clock held near a massive object runs more slowly when compared with a clock resting farther away. Around Earth, this difference is small, but precise instruments can measure it and navigation systems must account for it. Near a black hole, the same principle becomes one of the most dramatic features of the journey. Consider a small beacon descending toward the horizon while sending a steady pulse of light into distant space. At first, the pulses arrive regularly, and the beacon appears to move in an ordinary and predictable way. As it falls deeper, the pulses arrive farther apart and carry less energy than the signals sent before them. To a distant observer, the beacon seems to slow, redden, and fade as it approaches the invisible boundary. The distant observer never receives a final image showing the beacon clearly passing through the event horizon. Instead, later signals become so delayed and weakened that they eventually disappear beneath any practical limit of detection. The falling object does not remain visibly frozen as a bright and permanent picture on the edge of darkness. It becomes an increasingly faint memory carried outward by signals that take longer and longer to arrive. The experience of the falling object is very different from the distant observer's description of the same event. Its own clock continues to tick normally because every local process remains measured against the same nearby flow of time. For a sufficiently large black hole, the horizon may pass without any sudden flash, wall, or physical collision. The crossing occurs after a finite interval on the falling clock, even though the outside signals tell another story. These two descriptions do not contradict each other because time and simultaneity are not universal across curved space-time. Each observer organizes distant events using a different network of clocks, signals, distances, and gravitational conditions. The black hole exposes this relativity with unusual clarity because the horizon separates paths that can communicate from paths that cannot. What appears endlessly delayed from far away can still occur within ordinary local time for the object falling inward. The event horizon is not a shell made from matter, and it does not need to glow or resist contact. It is a boundary defined by the future paths available to light, matter, and every possible message. Outside the boundary, some future paths still lead away from the black hole and into the wider universe. Inside it, all future directed paths remain trapped, even when they point locally away from the center. Far from the horizon, a beam of light may be aimed in almost any direction and still escape. Closer to the black hole, the range of outward directions becomes narrower as more possible paths curve inward. At the horizon, the last outward path lies along the boundary and cannot increase its distance from the black hole. Beyond that point, even a beam directed outward moves toward a future located deeper within the hidden region. This strange behavior does not mean that light locally moves slower than its universal speed. Nearby measurements still find light traveling exactly as expected through the observer's immediate region of space-time. What changes is the geometry that defines where outward, inward, later, and farther can ultimately lead. The trap is built from the shape of space-time itself, rather than from friction, pressure, or a physical barrier. Most real black holes are expected to rotate because the stars and gas that form them already carried angular momentum. A rotating black hole has a more complicated geometry than the perfectly still black hole used in simple explanations. Its rotation drags nearby space-time around with it, an effect known as frame dragging. Close enough to the black hole, remaining completely motionless relative to distant stars, becomes impossible. Outside the horizon of a rotating black hole lies a region called the ergosphere. Within this region, matter and light are compelled to share some of the black hole's rotation. Escape may still be possible because the ergosphere remains outside the event horizon, but stillness is no longer an option. Space and time seem to flow around the rotating darkness like a current surrounding a hidden cosmic whirlpool. In theory, carefully arranged interactions within the ergosphere can remove a small part of the black hole's rotational energy. Astrophysical magnetic fields may also tap rotational energy and help power enormous jets from the surrounding plasma. The jets emerge from matter and fields outside the horizon, not from anything returning from the interior. Even the black hole's visible violence is therefore created at the edge of a region that remains completely silent. Gravity near a black hole can also stretch an object through differences in attraction across its length. The side closer to the black hole is pulled more strongly than the side only a short distance farther away. These tidal forces can lengthen matter in one direction while compressing it along the directions beside it. The familiar nickname for this extreme distortion is spaghettification, although the underlying physics is entirely serious. Near a small stellar black hole, tidal forces can become destructive before an object reaches the event horizon. Its horizon is compact, so gravity changes sharply across even a relatively short distance. Matter falling inward may be heated, torn apart, and mixed into luminous plasma long before the final crossing. The edge of such a black hole can be physically violent even when the horizon itself remains an empty boundary. A supermassive black hole can offer a surprisingly different experience near its much wider event horizon. Although its total gravity is immense, the change in gravity across a small object can be gentler at the boundary. An undisturbed falling object might cross that horizon before tidal forces become immediately overwhelming. The most important transition could occur without a local sign revealing that communication with the universe has ended. Once the horizon is crossed, no engine can create a path leading back to the exterior. The problem is not a lack of speed because every possible future direction has already been turned inward. Moving toward the center becomes as unavoidable as moving toward tomorrow while remaining outside an ordinary black hole. The horizon marks a change not merely in location, but in the structure of all remaining possibilities. From outside, we can study the light, heat, motion, and warped images gathered near this mysterious boundary. We can measure fading signals and describe the geometry that carries them toward us across the darkness. Yet the horizon preserves a final separation between what can still be observed and what can only be inferred. In the next part, we will follow time closer to this boundary and ask whether it can truly come to an end. Time seems to move quietly and evenly through ordinary life, carrying every moment toward the next without hesitation. We trust that distant clocks share the same steady rhythm, even when they are separated by oceans or planets. Near a black hole, that familiar certainty begins to dissolve as gravity separates one clock from another. The mystery is not that time becomes unreal, but that its passage depends on the path taken through space-time. For centuries, time was often imagined as a universal current flowing at the same rate everywhere in creation. Under that picture, every perfect clock would agree once differences in motion and mechanical error were removed. Modern relativity replaced this single cosmic rhythm with a universe where measurements of time depend on motion and gravity. There is no master clock hidden beyond the stars that announces one absolute present for the entire universe. Two observers moving differently can divide the same sequence of events into space and time in different ways. Each description remains internally consistent even when the observers disagree about duration, distance, or whether distant events happen together. Gravity deepens this relativity because a massive object changes the geometry through which every clock must travel. A clock near a black hole follows a different route through space-time from a clock resting among distant stars. A clock can be understood as any repeating physical process, not only a machine with hands or glowing numbers. An orbiting electron, a vibrating atom, a pulse of light, or a beating star can all mark duration. When relativity says a clock runs slowly, every process beside that clock shares the same local rhythm. Nothing nearby appears sluggish because thought, chemistry, light, and motion remain synchronized within that immediate region. The difference appears only when clocks that follow different paths are compared directly or exchange signals across space. One clock may record fewer seconds between two meetings, even though it never felt unusual during its journey. The measured duration carried by a clock along its own path is called proper time. Near a black hole, proper time becomes the quiet thread that follows an object through increasingly distorted geometry. Even Earth produces gravitational time dilation, although the effect is far too small for human senses to notice. A precise clock at a higher altitude ticks slightly faster than an identical clock resting closer to the ground. Satellite navigation systems must account for differences caused by both gravity and motion to maintain useful accuracy. What seems exotic near a black hole is therefore an extreme expression of physics already present around us. As a clock descends toward a black hole, it enters regions where space-time is curved more deeply. Compared with a clock far away, the descending clock accumulates less time between the same widely separated events. The difference grows gradually at first, then becomes increasingly dramatic as the clock approaches the event horizon. No invisible substance slows its gears because the difference belongs to the structure of space-time itself. Suppose a sequence of light pulses is transmitted from a stable platform held outside the horizon. A nearby receiver measures the pulses at their normal rhythm because both devices share nearly the same gravitational conditions. A receiver much farther away finds the pulses stretched apart and shifted toward lower frequencies. The expanding interval between pulses reveals the slower passage of the transmitting clock relative to the distant receiver. Signals sent downward produce the opposite comparison because light falling deeper into gravity arrives with a higher measured frequency. The lower receiver sees the distant clock running faster when its incoming pulses are compared with local time. Each observer therefore sees the other's signals altered by the gravitational landscape separating their locations. Their clocks remain locally ordinary, while the exchanged light carries evidence that their accumulated durations will differ. A traveler remaining close to a black hole could watch the distant universe appear to evolve at an accelerated rate. Incoming signals from far away would arrive compressed and shifted toward higher energies as the gravitational difference increased. Distant stars might seem to move more quickly, while external clocks would advance faster than the nearby clock. Yet this view would be complicated by distorted light, intense radiation, and the physical difficulty of remaining stationary. Remaining fixed above a black hole is not the same as floating freely through empty space. A hovering platform must continually accelerate outward to resist the natural inward paths created by gravity. The required acceleration grows without limit as the platform is positioned closer to the event horizon. No material structure can hover exactly on the horizon of a simple black hole while remaining motionless. The dramatic freezing of time at the horizon belongs to the description made by a distant stationary observer. It does not mean that all physical processes literally stop for an object falling through the boundary. The distant observer receives an endless sequence of increasingly delayed signals rather than witnessing a final crossing. In practice, those signals rapidly become too red, faint, and widely separated to detect against the surrounding universe. The falling clock experiences a simpler story because it follows gravity instead of continually resisting it. During free fall, the clock continues marking seconds normally while the event horizon draws nearer. For a sufficiently massive black hole, local conditions at the horizon can remain calm and unremarkable. The traveler crosses after a finite amount of proper time without encountering a solid surface or sudden interruption. Relativity allows both descriptions because they use different ways of assigning coordinates to distant events. Coordinates are labels placed on space-time, and some labels become poorly behaved at the event horizon. A suitable choice of coordinates describes the crossing smoothly and removes the appearance of a physical barrier. The horizon remains real because it limits communication, even though the apparent freezing depends on the chosen description. Before the crossing, an outward signal can still escape if it is emitted early enough and along a suitable path. Signals emitted later must climb from deeper gravity and reach the outside universe with less energy. At the horizon, the final outward path remains trapped along the boundary instead of moving farther away. After the crossing, every future-directed signal travels towards smaller distances from the center. Outside a black hole, moving inward or outward is usually a choice among different spatial directions. Inside a simple horizon, the geometry changes so deeply that decreasing distance from the center becomes unavoidable. Turning around cannot reverse this fate because every available future path continues farther into the hidden region. The center lies ahead in time as certainly as tomorrow lies ahead for someone living far from the black hole. This does not mean that space and time exchange identities in every simple or literal sense. It means that the causal structure no longer permits a future that remains at the same radius or moves outward. Every local clock still measures ordinary seconds, while the collection of possible destinations steadily narrows. The strangeness belongs not to local motion, but to the global shape connecting each moment with its future. For a non-rotating black hole, classical relativity predicts that the inward journey ends after a finite interval. The destination is described as a singularity where familiar measurements of curvature grow without bound. Most physicists interpret this prediction as evidence that classical relativity has reached the limit of its usefulness. A deeper theory involving quantum gravity may replace the singular ending with a structure not yet understood. A rotating black hole offers an even more complicated interior than the simple model used for this journey. Its equations contain additional horizons and regions where the mathematical roles of direction and causality become unfamiliar. Idealized solutions can suggest passages toward other regions, but those possibilities may not survive realistic disturbances. Small amounts of radiation and matter could make the inner geometry violently unstable before any such passage appeared. Scientists therefore separate what the equations permit under perfect assumptions from what nature is likely to create. Black hole interiors remain inaccessible to direct observation because no report can return after crossing the horizon. Our understanding is built from mathematics, external measurements, and the demand that physical laws remain mutually consistent. The result is a map of hidden time drawn entirely from evidence that remains outside the darkness. The absence of a universal present becomes especially unsettling when a horizon divides the universe into separate causal regions. An event beyond the boundary can be real for the falling object while remaining forever unavailable to distant observers. Reality does not require every event to be visible from every location or included within every observer's future. The black hole makes this separation permanent by shaping light itself into a boundary of knowledge. We often imagine the present as a thin surface extending across the universe at one shared instant. Relativity offers no unique surface that every observer must accept as the single correct cosmic now. Different motions and gravitational fields produce different ways of arranging distant events into past, present, and future. Near a horizon, these differences become impossible to ignore because communication itself is approaching an irreversible limit. A distant observer may describe the black hole as holding the fading history of everything that approaches its edge. The falling object instead discovers that the boundary passes and the remaining future continues deeper inside. Neither description provides a complete view from nowhere because physics offers observations only from particular paths. The universe is woven from relationships among clocks, signals, trajectories, and events, rather than one universal viewpoint. At the edge of a black hole, time has not vanished, but its familiar simplicity has disappeared. Seconds continue locally, while distant comparisons stretch those seconds across longer and weaker trails of light. The horizon does not stop the clock, because it changes which future destinations the clock can ever reach. Beyond it, the passage of time becomes inseparable from a journey toward the deepest unknown region. Classical relativity leads that journey toward a place where its own equations can no longer provide a complete answer. The singularity waits not as an observed object, but as a warning written into our current understanding. There, questions about matter, geometry, causality, and time gather at the boundary between known physics and something deeper. In the next part, we will follow those questions toward the hidden center and the limits of physical law. Beyond the event horizon, every future path leads away from the visible universe and toward a hidden center. No telescope can look into this region because every image and message remains trapped with the matter that created it. Our journey must therefore continue through mathematics, where physical laws describe a destination that observation cannot reach. At the end of that description lies the singularity, perhaps the deepest warning hidden inside a black hole. In classical relativity, collapse does not stop after matter crosses the event horizon of a sufficiently simple black hole. The remaining material continues inward while the available volume becomes smaller and the surrounding curvature grows stronger. The equations eventually predict conditions where familiar quantities become infinite or cease to have a clear physical meaning. That predicted failure is what physicists call a singularity, though the word can easily create a misleading picture. A singularity is often imagined as a tiny object sitting at the center of an enormous sphere of darkness. Classical theory describes something stranger because the singularity is not simply another location that a traveler could pass beside. It represents an ending of possible paths through space-time, where the geometry can no longer be smoothly continued. The destination is less like a hidden stone and more like a missing future in the structure of the universe. Physicists describe this problem through paths called geodesics, which represent natural motion through curved space-time. A freely falling object follows such a path without feeling a continuous force pushing it through its immediate surroundings. Near a singularity, some of these paths end after only a finite amount of time measured by the falling object. There is no later point within classical spacetime where the same path can continue in an ordinary way. Popular descriptions sometimes say that all the black hole's mass is compressed into a point of infinite density. This language captures the extremity of the prediction, but it should not be mistaken for a confirmed microscopic picture. Density depends on how volume and matter are defined in a region where ordinary geometry has already broken down. The safer conclusion is that classical relativity predicts its own inability to describe the final state completely. For an ideal non-rotating black hole, the singularity lies in the future of everything that crosses the horizon. It cannot be avoided by turning sideways because every allowed direction through space-time still leads toward the same ending. The geometry does not place the center merely below or ahead in space, but ahead in every possible future. Escaping it would require avoiding the passage of time itself after the horizon had already been crossed. As the inward journey continues, tidal forces grow because gravity changes across shorter and shorter distances. One side of a falling object is drawn inward more strongly than the side located slightly farther away. The object stretches along the direction of fall while being compressed across the directions surrounding that path. Closer to the classical singularity, these differences can grow beyond the strength of any known material structure. A supermassive black hole may allow a calm crossing because tidal forces can be mild at its enormous horizon. That temporary calm does not continue forever because the curvature increases as the journey approaches the hidden center. Distances that once seemed vast become compressed into a rapidly narrowing region of unavoidable gravitational change. The gentleness of the horizon therefore delays the destruction without removing the deeper problem predicted inside. Matter would first lose the large structures that once gave it shape, from planets and stars to smaller solid forms. Molecules could be separated, atoms stripped apart, and nuclei exposed to conditions far beyond any natural laboratory. At still greater curvature, even the descriptions used for particles and fields may require an unknown form of physics. The inward collapse becomes not only a destruction of matter, but a test of the concepts used to define matter. General relativity describes gravity with extraordinary success across planets, stars, galaxies, and the expanding universe. Quantum theory describes particles and fields with equally remarkable success across the smallest measurable scales. A singularity forces these two achievements into the same extreme region where neither theory can be safely used alone. The missing description is usually called quantum gravity, a theory that would unite geometry with quantum behavior. At extremely small scales, space-time may not remain smooth in the way classical relativity assumes. Quantum uncertainty could affect distances, durations, and curvature rather than acting only on matter within a fixed background. The scale where such effects may become unavoidable is often associated with the extraordinarily tiny Planck length. No experiment has directly revealed the full structure of space-time at that depth, especially inside a black hole. One possibility is that quantum effects prevent curvature and density from ever becoming truly infinite. The classical singularity might be replaced by a tiny but finite region governed by unfamiliar rules. Another possibility is that the very ideas of location, duration, and interior lose their ordinary meaning there. Scientists do not yet know which picture is correct or whether any current proposal captures the complete answer. Some approaches describe space-time as built from discrete quantum relationships rather than an infinitely smooth continuum. Others suggest that the fundamental ingredients of nature are extended structures whose behavior softens extreme concentrations. Certain models replace the classical center with a dense quantum core, a bounce, or a more distributed interior state. These ideas remain active possibilities, rather than confirmed descriptions of what exists beyond an actual horizon. The prediction of singularities does not depend only on perfectly spherical stars or exactly motionless black holes. Mathematical theorems show that under broad conditions, gravitational collapse can make incomplete paths difficult to avoid. These results helped establish that singular behavior was not merely an accident of one overly simple equation. They also depend on assumptions that quantum physics may eventually modify when curvature becomes sufficiently extreme. Classical theory often hides the singular region behind an event horizon, safely separating it from the outside universe. This expectation is related to cosmic censorship, the idea that nature generally conceals such failures from distant observers. If the principle is correct, unpredictable conditions near a singularity cannot directly send signals into open space. The horizon would preserve the ability of outside physics to evolve without receiving information from a broken boundary. A singularity without a surrounding horizon is sometimes called a naked singularity because its effects could remain exposed. Certain mathematical solutions allow such objects under special conditions, though their physical formation remains uncertain. Realistic collapse includes rotation, radiation, turbulence, magnetic fields, and disturbances that may prevent those ideal outcomes. Whether cosmic censorship always holds remains one of the subtle unanswered questions within classical gravitational theory. A rotating black hole changes the classical picture because its ideal solution contains a ring-shaped singular structure. The surrounding interior contains additional boundaries and a geometry more complicated than the simple non-rotating case. In the perfect mathematical solution, some paths appear to pass through the ring toward other regions of space-time. Nature may never permit that delicate structure to survive the smallest realistic flow of matter or radiation. The inner horizon of a rotating black hole can receive radiation that has been enormously amplified by the geometry. Even a faint disturbance may grow into an extreme concentration of energy as different streams cross one another. This instability may transform the elegant ideal interior into a violently curved region before any passage can form. The leading expectation is therefore more cautious than the strange possibilities suggested by the undisturbed equations. Black holes are often connected with wormholes in stories about tunnels linking distant regions of the universe. Some equations contain bridge-like geometries, but these structures are not known to be stable or traversable in nature. An ordinary astrophysical black hole does not provide a demonstrated doorway that safely opens somewhere else. According to current understanding, falling inward leads toward extreme curvature rather than a usable cosmic passage. A white hole is another mathematical possibility, defined as a region that matter can leave but never enter. It resembles a black hole with the direction of time reversed within an idealized solution. No confirmed astronomical observation has shown that white holes exist as long-lived objects in the real universe. Their role remains theoretical, useful for exploring equations without proving that nature creates the same structures. The black hole interior is mysterious because its center is not merely hidden somewhere at a great distance. It lies at the end of every future available after crossing, making location and destiny difficult to separate. A falling object does not simply approach a place because its remaining time becomes part of the approach itself. The singularity is therefore described through the ending of possible histories rather than an image seen from outside. Everything that formed the black hole carried information about particles, motion, temperature, fields, and countless earlier events. Classical collapse seems to carry those details toward a region where the theory no longer explains their future. Quantum physics suggests that information should not simply vanish from the complete evolution of a closed system. The tension between these ideas prepares one of the most important puzzles in modern theoretical physics. Words like center, point, density, and ending come from ordinary experience within smooth and measurable space. Near a predicted singularity, those words may survive only as approximations carried beyond their reliable domain. Mathematics can reveal that a theory has reached a boundary without describing what nature places beyond that boundary. Recognizing this limit is not a failure of science, but an honest description of where knowledge remains unfinished. The singularity asks whether reality can contain an absolute end, or whether every apparent end hides deeper structure. It asks whether space and time are fundamental, or whether they emerge from something more ancient and less familiar. It also reminds us that the universe is not required to preserve the categories human intuition finds comfortable. At the deepest interior, even the question of what happens next may need to be asked in another language. For now, the singularity remains a silent boundary drawn by equations and hidden behind an unreachable horizon. It may be a physical state, a quantum transition, or simply the place where classical geometry stops speaking. Whatever replaces it must explain not only gravity and matter, but the fate of every detail carried inward. In the next part, we will follow that information and ask whether anything swallowed by darkness can truly disappear. A black hole can swallow stars, gas, radiation, and every intricate pattern carried within them. From the outside, all that complexity seems to fade behind a horizon that reveals almost nothing. Yet, quantum physics suggests that the full history of a physical system should never simply disappear. Between these ideas lies the black hole information paradox, a mystery where gravity and quantum theory quietly collide. In everyday language, information may mean words, memories, images, or messages carried from one mind to another. In physics, the meaning is broader and includes the precise arrangement and state of every part of a system. The positions, motions, energies, charges, and quantum relationships among particles all contribute to that physical information. Even a simple cloud of gas contains an enormous description hidden within the motion of its countless atoms. When two physical systems begin differently, their later states should preserve some trace of that original difference. The details may become mixed beyond practical recovery, but they are not expected to be erased from reality. A shattered object appears to lose its earlier form, although the fragments still carry the consequences of what happened. Quantum theory extends this principle to the deepest description of isolated systems evolving through time. A classical black hole appears remarkably simple when measured from the distant universe surrounding it. Its exterior gravitational field can be described mainly by its mass, rotation, and electric charge. The countless details of the collapsing star seem to become invisible once they pass beyond the event horizon. This apparent simplicity is often summarized by saying that a settled black hole has very little external hair. Two stars with different compositions could collapse into black holes, sharing the same mass and rotation. After the surrounding disturbances fade, their exterior geometries could become almost impossible to distinguish. The black holes would not openly reveal which atoms, fields, and histories had created their hidden interiors. For classical gravity alone, this concealment creates no immediate contradiction because the information can remain behind the horizon. A deeper clue appeared when black holes were found to behave like objects possessing temperature and entropy. Entropy measures how many hidden microscopic arrangements can correspond to the same visible, large-scale condition. A warm gas has high entropy because countless molecular configurations can produce the same pressure and temperature. If black holes have entropy, their simple exterior may conceal an extraordinary number of possible internal states. The surprising result is that black hole entropy is proportional to the area of the event horizon. Ordinary intuition might expect the hidden information capacity to grow with the volume enclosed inside. Instead, the relevant quantity is measured across the two-dimensional surface separating the interior from the universe. This connection between information and area became one of the strangest hints offered by black hole physics. When matter falls into a black hole, the horizon usually grows and its area increases. The increase resembles the ordinary law stating that the total entropy of an isolated system should not decrease. Black hole mechanics began to resemble thermodynamics even before anyone believed the resemblance was physically complete. Then, quantum theory revealed that the analogy was not merely mathematical because black holes can possess a real temperature. Quantum fields do not become perfectly silent in the empty space surrounding an event horizon. Their fluctuations are shaped by the curved geometry and by the difference between observers near and far away. A distant observer can describe the black hole as emitting a faint thermal glow known as Hawking radiation. The radiation arises from quantum fields across the changing space-time, not from ordinary light escaping the interior. A popular picture describes particle pairs appearing near the horizon while one falls inward and the other escapes. That picture can offer intuition, but the complete calculation concerns quantum fields spread across curved space-time. The escaping radiation appears thermal, carrying a temperature determined by the black hole's gravitational properties. From far away, the darkness is no longer perfectly dark, although its glow can be almost unimaginably weak. Larger black holes are colder, while smaller black holes possess a higher Hawking temperature. A black hole with the mass of a star is far colder than the faint background radiation filling the present universe. Today, such a black hole absorbs more surrounding energy than it loses through its own quantum emission. Only in a much colder future would isolated black holes begin losing mass faster than they gain it. Hawking radiation carries energy away, and the black hole must gradually surrender an equal amount of mass. The process is extraordinarily slow for known astrophysical black holes because their temperatures are so low. A stellar black hole would require vastly longer than the current age of the universe to evaporate completely. A supermassive black hole would persist for an even more remote span before reaching its final stages. As the black hole loses mass, it becomes smaller, hotter, and increasingly efficient at radiating energy. The long era of near silence slowly gives way to a faster and brighter final phase. The last moments depend on unknown quantum gravity, so the exact ending cannot yet be predicted with confidence. The black hole may disappear entirely, leave a remnant, or transform through physics beyond current theory. The paradox appears when Hawking radiation is treated as perfectly thermal and unrelated to what originally fell inward. Thermal radiation is characterized mainly by broad quantities such as temperature rather than detailed microscopic history. If the black hole evaporates completely, the hidden interior may vanish while only featureless radiation remains. Different initial objects could then produce the same final radiation, erasing the distinction between their earlier states. Quantum mechanics normally evolves a complete state in a way that preserves all information contained within it. This preservation is called unitarity, and it allows the present state to retain a connection with the past. True information destruction would break that structure and make fundamental evolution depend on irreversible erasure. The consequences could spread beyond black holes and disturb the consistency of quantum theory itself. One possible answer is that Hawking radiation is not exactly featureless when every subtle quantum correlation is included. Individual particles could appear random while the complete pattern among them quietly preserves the missing information. The information would emerge in an extraordinarily scrambled form, spread across radiation released over immense periods. Recovering it might be practically impossible, even if no fundamental detail had truly been destroyed. This distinction separates information that is lost in principle from information that is merely impossible to reconstruct. A burned page is difficult to restore, yet its physical influence survives among ash, heat, light, and surrounding air. A black hole may perform a vastly more complete form of scrambling without carrying out genuine erasure. The challenge is explaining exactly how the horizon and radiation accomplish this while respecting known physics. The area law inspired the holographic principle, which suggests that a region may be described by information on its boundary. A volume of space could possess a complete description using fewer dimensions than ordinary intuition expects. In certain theoretical settings, gravity within a region is mathematically equivalent to a quantum theory on its edge. These relationships strongly suggest that black hole evolution can preserve information in a complete quantum description. Black hole complementarity offers another viewpoint in which no single observer witnesses a direct violation of physical law. From outside, information may appear encoded near the horizon and eventually released through quantum radiation. For a freely falling observer, the horizon may remain locally ordinary while the information continues inward. No observer can compare both copies directly because communication across the horizon allows only one-way travel. This delicate picture faces pressure from quantum entanglement, the deep relationship connecting separated parts of a system. Late Hawking radiation may need to be correlated with earlier radiation if the complete information is to escape. The same late radiation also appears connected with partners behind the horizon in the simplest semi-classical calculation. Quantum entanglement cannot be shared without limit, creating a conflict among several cherished principles. One proposed response is a firewall, a violent layer of high-energy activity located near the event horizon. Such a structure could break the interior entanglement and allow the outgoing radiation to preserve information. It would also destroy the expectation that a large black hole horizon feels locally calm to a falling object. Whether firewalls exist remains debated, and no direct observation has revealed such a boundary. Another clue comes from tracking how entanglement should change during the full lifetime of an evaporating black hole. If information is preserved, the entropy of the radiation should first rise and later fall toward a pure final state. This expected rise and decline is known as the Page curve, named for the physicist who studied it. The turning point suggests that later radiation must gradually reveal correlations with what escaped before. Recent theoretical calculations reproduce the page curve by including regions called islands in the entropy calculation. These islands are portions of the black hole interior that become encoded within the description of distant radiation. The result offers strong evidence that gravity can reorganize what counts as the information belonging to the radiation. It does not yet provide a complete practical account of evaporation for every realistic black hole in our universe. The leading direction in modern theory is that information survives, although its path remains deeply hidden. A black hole may not be a final grave for physical history, but an extreme machine for transforming it. What enters as stars, fields, and ordered matter may leave as correlations scattered across nearly featureless radiation. The original pattern could remain present without ever returning in a form that the universe can easily recognize. Black holes therefore connect the smallest quantum relationships with the largest and most powerful structures shaped by gravity. Their fading glow suggests that even darkness has a temperature, a lifetime, and a final conversation with the universe. When the last black holes begin to vanish, the cosmos will enter an age more distant than any familiar measure. In the final part, we will follow that fading darkness toward the remote future and the quiet end of cosmic time. The final age of black holes begins long after the familiar stars have faded from the expanding universe. Galaxies that once blazed with crowded light become dark islands separated by distances that continue to grow. Within those quiet remnants, black holes endure after most ordinary sources of warmth have disappeared. Their long survival carries our journey beyond stellar history and toward the deepest future that physics can imagine. The universe is already expanding, and distant galaxies are gradually carried away from one another by changing cosmic space. According to current measurements, this expansion is accelerating under the influence of something described as dark energy. Scientists do not yet know the fundamental nature of dark energy or whether its behavior will remain unchanged forever. The leading simple picture suggests that the large-scale universe will continue becoming colder, emptier, and more isolated. Stars continue forming only while galaxies contain enough cold gas to gather into dense and collapsing clouds. Over immense periods, that useful gas becomes locked inside stars, scattered by explosions, heated, or captured by compact objects. The birth rate of new stars declines until only a few faint suns appear within the remaining galactic darkness. Eventually, the final ordinary stars exhaust their fuel, and the long, luminous era of the cosmos comes to an end. What remains is a population of stellar remnants that no longer shine through sustained nuclear fusion. White dwarfs cool slowly, neutron stars lose their remaining heat, and failed stars become almost perfectly dark. Planets may continue orbiting these remnants for extraordinary durations, although their surfaces receive almost no natural warmth. The universe becomes filled less by visible objects than by gravity, motion, memory, and widely separated matter. Even stable orbits do not guarantee that every object will remain inside its original galaxy forever. Repeated gravitational encounters can exchange energy, sending some remnants inward while throwing others into intergalactic space. Given enough time, many galaxies may gradually dissolve as their smaller members escape into the expanding darkness. The heaviest objects tend to sink toward the center, where black holes may merge and continue growing. During this remote era, black holes become some of the largest concentrated reservoirs of mass remaining in the universe. They may consume wandering stars, cold remnants, thin gas, and smaller black holes that pass close enough. Each capture briefly disturbs the surrounding darkness before the new material settles behind the growing event horizon. After the last available matter is scattered or swallowed, even these enormous objects enter a quieter stage. A black hole without nearby gas produces no bright disk and no powerful jet to mark its presence. It moves through almost empty space, surrounded only by thin radiation and the faint gravitational influence of distant remnants. Its exterior remains simple and dark, while the expanding universe carries other surviving structures increasingly far away. For an almost unimaginable interval, the black hole appears unchanged, as though darkness itself had become permanent. Yet Hawking radiation means that an isolated black hole is never completely separate from the quantum fields surrounding it. The horizon gives the black hole a temperature, although that temperature is extremely low for an astrophysical object. While the universe remains warmer than the black hole, more background energy is absorbed than released. As cosmic space expands and the background cools, a distant time arrives when the balance finally reverses. The black hole then begins losing slightly more energy than it receives from the surrounding universe. Its mass decreases by an amount so small that no ordinary comparison can capture the patience required. A stellar black hole survives vastly longer than stars, planets, and the present age of the cosmos. A supermassive black hole endures even longer because increasing mass lowers its temperature and slows its evaporation. Time passes through stretches so immense that the earlier universe becomes almost impossible to recognize in the remaining conditions. The galaxies of the stellar age survive only as dispersed remnants, distant particles, and information carried through fading radiation. Against this nearly empty background, the slow loss of a black hole becomes one of the universe's final active processes. The darkest objects in cosmic history become some of the last objects still producing new radiation. Evaporation accelerates because a shrinking black hole becomes hotter as its mass continues to decline. The faint emission gradually strengthens after an era that was dominated by almost complete stillness. Radiation leaves more quickly, the horizon contracts faster, and the remaining lifetime becomes progressively shorter. What began as a nearly eternal whisper slowly develops into the final brightening of the ancient darkness. The exact final stage remains uncertain because the black hole eventually reaches scales where quantum gravity must become important. Classical geometry and ordinary quantum fields cannot provide a complete description of those last extreme moments. The ending may involve a brief release of energy, a tiny remnant, or another transition not contained in present theory. What remains clear is that the familiar black hole cannot continue unchanged after almost all its mass is gone. Smaller black holes complete their evaporation first, leaving the most massive black holes to dominate the final era. The giants that once occupied galactic centers remain after the galaxies around them have been scattered or transformed. One by one, those surviving horizons also shrink until the universe approaches the disappearance of its last black hole. The final darkness releases its remaining energy into a cosmos that has waited through nearly inconceivable time. After the last black hole is gone, no event horizon remains to divide a hidden interior from the surrounding universe. There may be no stars, no warm planets, and no concentrated objects capable of organizing matter on familiar scales. Only extremely dilute particles and radiation continue moving across a space that has grown extraordinarily large. The universe has not necessarily ceased to exist, but almost every ordinary source of visible change has disappeared. This possible future is often associated with heat death, a state where usable differences in energy have nearly vanished. Engines, stars, weather, chemistry, and life depend on energy flowing from concentrated regions toward less concentrated surroundings. When matter and radiation become too evenly dispersed, there is little free energy available to create complex transformations. The cosmic future becomes quiet not because motion stops, but because meaningful contrasts become increasingly rare. Photons may continue crossing the expanding universe, while their wavelengths stretch and their energies steadily decline. Neutrinos and other surviving particles may travel through regions so empty that encounters become almost impossible. If protons eventually decay, as some theories allow, even ordinary matter may slowly dissolve into lighter particles and radiation. Proton decay has not been observed, so this part of the remote future remains scientifically uncertain. Whatever particles survive, they may still carry quantum relationships inherited from processes that occurred in the ancient universe. The history of vanished stars and evaporated black holes could remain encoded within correlations spread across impossible distances. Information may persist without forming a readable archive or reconstructing the objects that once carried it. The universe can preserve consequences while allowing every familiar pattern to become dispersed beyond practical recovery. A star is more than its particles because its identity depends on a temporary arrangement maintained by gravity and energy. A galaxy is also a passing structure, assembled from countless motions that slowly change across cosmic time. Black holes appear permanent only when measured against lifetimes much shorter than their own. From the widest perspective, even an event horizon may be a temporary chapter within a changing universe. The direction of time is closely connected with entropy and the tendency of usable energy to spread. We remember the past rather than the future within a universe that began in an unusually ordered condition. Stars shine, objects age, and black holes grow or evaporate as entropy generally increases across larger systems. In a nearly featureless final state, the physical arrow of time may become increasingly difficult to recognize. Time could still remain part of the equations even when almost nothing exists to serve as a useful clock. Without repeating processes, observers, or changing structures, duration loses the practical meaning it has in the present cosmos. 1 trillion silent intervals would be physically distinct from one interval only if something remained capable of marking the difference. The end of cosmic activity is therefore also a question about what it means for time to pass. This distant picture depends on physical laws extrapolated far beyond any era that observation can directly test. Dark energy may change, new particles may exist, and quantum gravity may reshape the final stages of black holes. The vacuum of space may also possess properties that current experiments have not yet revealed. The remote future remains a reasoned possibility rather than a witnessed destination or a perfectly settled prediction. Black holes guide this exploration because they bring together gravity, quantum theory, thermodynamics, information, and the meaning of time. No other known objects place so many fundamental ideas along one invisible and irreversible boundary. Their birth reveals the strength of gravity, their horizons reveal the structure of causality, and their evaporation reveals quantum uncertainty. Their mysteries are not isolated puzzles, but connected questions about how the universe preserves and transforms reality. A black hole teaches that seeing is not the same as knowing because some regions cannot return an image. It teaches that time is not one universal rhythm shared identically by every path through the cosmos. It teaches that apparent destruction may conceal a deeper transformation whose details are scattered beyond recognition. Most of all, it teaches that the limits of knowledge can become visible even when their hidden side cannot. The end of the black hole era would not resemble a final curtain falling across a crowded cosmic stage. It would arrive after the stage had emptied, the lights had faded, and almost every structure had quietly dissolved. The last horizon would shrink within an expanse already too large and dark for any distant witness. Its final radiation would join the ancient light of everything else and continue into the widening silence. Beyond light and time, there may be no hidden kingdom waiting inside the darkness, only deeper laws not yet understood. The black hole remains powerful because it transforms absence into a boundary where the foundations of physics become visible. Its darkness carries the memory of stars, the shape of space-time, and questions that may outlive every civilization. And in the quiet universe beyond the last horizon, the mystery remains, even after the final light has gone.